Syzygy, episode 72, Nobel Black Holes. Hello and welcome back for another edition of the Syzygy podcast. I'm joined as usual by my colleague in astronomical crime, Emily Brunsden. Emily's sitting on, why are you sitting on your sofa? Can I see you on your sofa there in your living room?
Yeah, I'm chilling out
Across
here.
the other side of York
Looking
from
really
me.
cozy.
For once, we're actually in the same town, Emily and I. But because of, waves, hands, all this, we can't be in the same place at the same time because that would be just a little bit too sort of virusy. So we're going to avoid that. I'm in my office. Emily's in her living room. Emily, how you doing?
I'm doing pretty well, yeah. It's been interesting, heading back to the university a couple of days a week. It's been nice to see all the students back again. The students are very, very happy to be away from their parents as well, which I think makes everyone really rather happy.
It's strange times as well. It must be a very odd, a big shout out to all of the students, any of the students who are listening to us, because it's got to be a weird time to be starting university right now. I know that you, Emily, and all the other academics in the world are working really hard to make it all work and feel good and still be exciting for everyone who's starting their university studies. But it's not business as usual, is it?
It's absolutely not.
Yeah, very odd. So anyone who is out there starting up your degree, well done. Keep going. We're going to get through this one together. But listen, that's not what we're here to talk about today, are we, Emily? We're not here to talk about viruses. We're here to talk about something else exciting that's going on in the world at this point in time. It's always fun to get to a podcast around October time because October in the world of science means Nobel Prizes. It's Nobel Prize time.
It's the season.
And over the course of a week, a bunch of different prizes get announced. I think they start with medicine and then physics. Anyway, I can't remember the order. It's medicine and chemistry and physics, and there's literature in there and peace and important things like that. But we're concentrating on the physics one today because this year it's all about the black holes. This year is all about the black holes. There's the Nobel Prize is allowed to be given to up to 3 people, and it can be actually even split in half, which is confusing. How do you have split in half between 3 people? This year they've given half of the prize to one person and the other half to 2 people. But it's all about black holes. Emily, can you bring us up to speed? Who's won the Nobel Prize this year and why?
So super excitingly, and I think maybe we were just having a chat as we started that astrophysics seems to be really pulling its own weight now through the Nobel Prizes because we've got an astrophysics Nobel Prize this year. We had another one last year where we had exoplanets.
It's been huge, actually. If you look back through the last 10, 20 years, like how many of the last 10 years worth of physics Nobel Prizes has gone to astronomy, astrophysics, cosmology?
Yeah, well, I did a quick count, and I guess if you sort of loosely consider neutrino flavor oscillations as being astrophysics, which
I think we can claim
you can
that.
make the argument.
Totally.
Then, about half of the Nobel Physics Prizes have been
half of the physics Nobel Prizes in the last decade have gone to something that we will rightly claim as our own on this podcast. So it's a boom time for astronomy, astrophysics, cosmology, and all of that. And this year it's happened again, and this time it's black holes. So who got the gong this year?
So we've got the first half of the prize goes to Roger Penrose, and I'm gonna read the actual citation here. So this is for the discovery that black hole formation is a robust prediction of the general theory of relativity.
Mm-hmm. So that's prediction of black holes. It's a thing. Yep.
And the other half is split evenly between Reinhard Genzer and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy.
And it's nice. That's a really nice division of the prize because the first half of the prize goes for, hey, so black holes should exist, and the second half of the prize goes for, yeah, we know, we found one in the center of the galaxy. So that's really cool, and that's why it's been split down the middle of the theoretical and then the experimental, which is really cool. It's not even the first time this decade that black holes have received the Nobel Prize. Not the black hole themselves. The black hole doesn't get the Nobel Prize, obviously. Researchers get the prize.
Yeah, I'm pretty sure the researchers can do better things with the prize money than the black hole can.
I think they probably can just suck it up and disappear it out of existence. But yeah, it was LIGO, and LIGO detected its first detection was it two black holes spiraling in on each other and in a
That's right,
cataclysmic explosion of mutual destruction.
Merging event.
Yeah. So I mean, it's not just that 5 out of the last 10 years have been astrophysics. It's that 2 out of the last several years have been specifically black hole related. It is a big time in history for black hole physics. But what's interesting to me is that this story about black holes and their prediction and discovery, we're going back quite a way here. Like this is not something which has just come up in the last couple of years. The story of this particular Nobel Prize and the story of black holes it's getting on a bit. It's been around for quite a while.
It has, and it involves some of the biggest names in physics throughout the whole story as well, which is really, really exciting. So I think it was really nice to kind of review when we talk about Roger Penrose's contribution to black holes, sort of where that sits in the timeline of our understanding of, okay, where did we go from kind of writing down some equations to trying to solve those equations and then actually getting out there and finding these objects.
Yeah, I don't know about you, Emily. I mean, you're probably a lot closer to this than I am as someone who's sort of just an observer in the field. But something like black holes to me, I mean, it's such a central part of, I don't know, modern popular physics and popular culture. You know, it's in movies, it's all over the place. It's something which we've sort of absorbed culturally that I get really confused about. Like, so hang on, how long have we known about or thought these things might have existed? And I kind of feel like, but we've thought that these things have been there like forever, haven't we? Like, surely it was Newton or someone like that who came up with the idea. and it wasn't. Like, it's not a really old idea. But then at the same time, something like a black hole sounds like a really modern, crazy idea. And it's not really modern either. It's older than you think. So when did the notion of black holes like get invented?
Well, it's interesting because we call the sort of period in time when black holes sort of popped into existence, shall we say, at least into our physics notebooks and textbooks. We call this area of physics modern physics, which is always a little bit of a kind of misnomer because you'd think that means like all the stuff we've discovered in the last sort of 15, 20 years. And even maybe that's not a good enough definition of modern for young people today.
The modern era.
But modern physics generally refers to physics that was primarily developed in the early part of last century. So we're talking about like 1900 to 1920, 1930, which is, I mean, we need a new name. It's getting on a bit, right?
Yeah, it's Einstein, it's quantum, it's a lot of statistical mechanics. There's a lot of stuff which grew out of new ideas that really sort of bore fruit like 100 years ago. And that's modern physics. I mean, it is one of the weird things about studying physics at school and then at university is that it takes you years just to catch up with last century. You know, it takes you a really long time to start getting to grips with stuff. It's like, you know, well done, congratulations, you've now caught up with the 1920s. Good work, excellent. So we're going back to what? Sort of Einstein's general theory of relativity,
exactly,
I guess.
Yeah.
When was that?
1915 that Einstein sort of published his general theory of relativity. And we should, I guess, take a moment to remind ourselves what general relativity means, because it's pretty significant. And it's the controversial thing that Einstein never got a Nobel Prize for this particular piece of research. He got it for
bit embarrassing.
photoelectric effect, which is important, but arguably not as important as GR.
Well, I had heard from a few people who were, I don't know, considered themselves to be in the know, that no Nobel Prizes were given for anything even vaguely related to general relativity for a really, really long time because of that embarrassment. Because, we can't give it to you because Einstein never got one. Like, we're just look in completely different areas of physics for someone deserving of the prize because we can't even go near this one. Clearly, after 100 years, that era is over and people are getting general relativity related Nobel Prizes left, right, and centre. I mean, we should be getting one any day now, Emily, I reckon.
Oh yeah, I'm just waiting for the call. So, interestingly, Einstein proposed his theory of general relativity. Now, general relativity was kind of he did worked on something called special relativity first, and special relativity talks about how things change when you move them at very, very high speeds. So we're not talking about kind of like motorway speeds or like airplane speeds. We're talking about when you move objects that have mass close to the speed of light, crazy physics happens, basically.
Yeah, weird
You
stuff.
get changes in how big they are, you get changes in how massive they are. Everything is relative to how fast you are moving, and that's therefore the relativity kind of part of special relativity.
Yeah, and it really played with the world's sense of space and time. This is where our notion of space and time being sort of a background arena in which everything in the universe plays out got turned on its head, because suddenly space and time are like they're an active participant in the whole process. That space can change, time can change depending on how fast you're moving relative to someone else. It's not absolute. My time and your time can be and are different because we move differently. So that was all really weird, but that was special relativity. And then a couple of years later, he came along with general relativity and said, hold my beer, this one, like you thought that was weird, this one is really going to knock you for six. The general theory of relativity, what did that do, Emily? What did that introduce?
So that introduced the idea that some of the physics changes depending on how close you are to massive objects. Or equivalently, flipping that around, you can say that massive objects change not only kind of the way that other objects interact with them, but they actually change the whole fabric of space and time in the universe as well. And it's orders of magnitude harder than special relativity.
It sure is. I remember studying and I just spent the entire lecture series just going, what? That doesn't make any sense. So if special relativity said space and time, not what you thought, general relativity turned around and said, yeah, look, space, time, mass and energy, they're all intertwined, and massive or energetic objects warp the space and time around them, and that can have crazy weird effects on the way we experience the universe. So that was 105 years ago.
Amazing,
when
yeah.
he came out with that one. But as you said, it's really hard mathematics, right?
It's really hard.
So in order to figure out what general relativity means, what the implications of that mathematics is for the universe around us, that's really hard. It's hard stuff.
It is, yeah. The special relativity you can kind of boil down to a couple of equations that, first-year physicists can cope with quite easily. You just got to put some numbers in, do a bit of division, do a square root, and you're there. General relativity, you need to have a whole new set of mathematics that you don't learn at school. That you need to go to university to learn this kind of how to deal with mathematics in 4 dimensions before you can even tackle GR.
Yeah. Four-dimensional curved space-times and tensor calculus and all sorts of just, nasty stuff. But that's not important. The details of the mathematics are not important for this discussion here today. How do you get from Einstein going, here it is, here's my general theory of relativity, to black holes in, at most, 3 moves? Off you go, Emily.
Well, it actually only took a famous physicist called Schwarzschild about 6 weeks once Einstein announced his discovery.
That's pretty good. That's pretty good. Einstein comes out and says, here's a theory, have at it. And Schwarzschild went, hang on a second, give me a minute. Here you go. Here's an interesting result. And that's not to be sneezed at, because as we said, these are very, very difficult and very strange calculations. But what did Schwarzschild do? What did he come up with?
So he was able to solve some of the tricky field equations that Einstein had put together. And he found out that there were 2 really weird points in these equations. So you're considering an enormous mass in a restricted area. And he found out that when the radius is equal to 0, then you get weird physics happening. Kind of the equations start to break down. They go crazy. And there's a second point, which is when you at a particular radius from the center of the object, which we now call the Schwarzschild radius. You get some crazy mathematics going on. And these are both were identified at the time as singularities, which means just maths gone insane.
Yes,
really
singularity
weird
is a nice mathematical and physical term for it broke. Sorry, broke that one. But it's really interesting, right? And particularly when you've got very complicated, very tricky mathematics, one of the best ways to approach that initially is to say, all right, well, if we can clear away all of the messy stuff, are there any solutions to these equations? Are there any special cases that we can investigate and get at? Even if they're meaningless, even if they're stupid, can we just wrench anything out of these at all? And that sounds like that's what Schwarzschild did, is he said, well, can we solve this at all? What can we do? If we get close to a very massive thing, then we find that there are these weird places, the Schwarzschild radius, where the mathematics just goes a bit hog wild. And that's interesting. It might mean that the whole thing's broken, or it might be trying to tell us something about the universe. And it was kind of the latter, wasn't it?
Definitely, yeah. So after a while, and a whole lot of other mathematical physicists having a crack at these sort of theories, then everyone came to the conclusion that the point at a radius equals 0, the center of this object, is a true singularity. It's just a mathematical glitch in the universe. And this is what we now call the center of the black hole.
Right.
The other point, which is very interesting, we call the Schwarzschild radius, and this is turns out to be the point of no return. In a simple black hole, we also call this the event horizon, where this is a point where the mass of the object is so great, the force which pulls in even a photon, which can travel at the speed of light, is greater than the escape speed that the photon can have as the speed of light. So the photon's not going fast enough to escape. The object gets sucked in and it's inside the black hole forever.
Right. So that must have, at the time, been a bit of a brain melt for the physics community, because we haven't had terribly much time. We've gone from a very classical view of the universe to no, it's all about warped space-times and weird tensor algebra, says Einstein. And then people then start talking about, you know what, under these very special circumstances, you might get a little bit of the universe that kind of closes itself off from the rest of the universe. You might have this little pocket in which, if you get enough concentration of mass and or energy, basically the same thing, thanks Albert, then once you get inside there, you can't get out again. Nothing's coming out from this little pocket inside this radius. And that's a very odd idea. Was it taken seriously, do you think, at first? Or was it just sort of, you're off your nut?
Well, it was kind of viewed as a mathematical oddity. Like, this is kind of, this is a cool thing if you shove weird numbers into this equation and you get a weird result. Einstein himself very famously never really believed that these objects would exist as what we call black holes in the universe. But they thought it was just either kind of just a weird part of the equation. Maybe if you had a bit more extra parameters in the general relativity, it would go away, or maybe it just means that these objects just don't exist and they're only hypothetical and there's no way to create them. But interestingly, a few people started thinking about, well, how could we create these weird objects? And this again builds on some interesting stuff. Some people were looking at things like they called dark stars, all the way back in the 1800s, late 1800s, because it's just an idea. How big a star can you possibly get before it collapses in on itself? That's a very I think natural question for a stellar astronomer to ask themselves when they're thinking about different sizes of stars.
Yeah, I mean, well before any of these ideas around relativity came around, it was still, I'm guessing, understood that if you've got a big red or hot object in the sky, a star, then how is that held up? You've got mass pulling in due to gravity, which we've known about for hundreds of years, and you've got the pressure of all the radiation coming outwards, and so you reach this balance. But you're able to then ask the question, well, surely if you keep making this bigger and bigger and bigger, eventually the gravitational pull gets too big. So you can talk about that way before we have much of the other information that we've gained over the last 100 or so years about stars and relativity and all of that sort of thing. So they were doing that well over 100 years ago, right?
Yeah, exactly. And then it was kind of when those ideas started to get put together. So one key player was Oppenheimer, of course, atomic weapons.
Yes,
fame.
infamous Oppenheimer.
Or infamy, if you might like. But in the 1930s, before World War II, Oppenheimer was looking at very, very massive stars collapsing. So these are our kind of supernova events. And he was looking at, well, if your star is massive enough, then even after the supernova, then you've got too much mass, and that mass is just going to collapse down in on itself. And he started drawing together some of these ideas coming from the mathematical physics community as well, and starting to put together, oh, maybe these things start to form these weird, objects, which still weren't quite called black holes then, but, called these singularities.
So that's sort of given us a bit of background. We've gone from even pre-Einstein ideas of dark stars and how big can a star be. You've got Einstein laying out the mathematical framework for a new view of mass, energy, space, and time. You've got Schwarzschild coming along saying, so there's this radius and this central point, which are pretty weird. We should look into those. You've got Oppenheimer making some calculations going, supernovas, dying stars, this could happen. Where does Penrose come in? We should probably get back to him, given that he's the one who's won half of the Nobel Prize for this stuff.
Oh, hang on, he's got to wait his turn. He's got some giants' shoulders to stand on.
Oh, okay, we've got more giants. Forgive me.
He's got to stand on these giants' shoulders.
Who's next?
We've got more giants.
Giants everywhere.
Well, then in the story, we started. This would be a great novel. Then we started finding some weird objects in the universe. And this was in the 50s and 60s. And these objects are called quasars.
I see. So we start getting observational now.
Now, quasars were these very bizarre objects. They looked like a star. They're called quasi-stellar objects. They looked a bit like a star, but didn't really behave like a star. And so they're basically very, very red-shifted objects. And once we sort of figured out that these were incredibly redshifted objects, we figured out that must mean that they're very, very, very far away.
Okay, now backing up on that a second, redshifted. So let's just remind ourselves of what that means. They're looking up in the sky and they're seeing, it kind of looks like a star because it's bright and shiny, I'm assuming, but it's redshifted. What do we mean by that?
So that means that instead of seeing the light in, say, let's say we're looking for hydrogen. If we look at hydrogen, then in the normal part of the spectrum, it falls in just kind of towards the red part of our spectrum, just inside the visible range. But when you see that object at a very, very large distance, then because the expansion of the universe has sort of pulled the photon as it's traveled between that object and us, it's stretched it out and made it a lot redder. So what used to be kind of just in the red part of the optical spectrum has now been shifted all the way down into the infrared part of the spectrum.
Which is weird. So you've got this strange object in the sky, which it's got fingerprints of things like hydrogen in it. It's got stuff that we understand and we can recognize, but it's shifted way, way, way down to the red side, which means our interpretation of that is it's a really, really long way away. And these were a really long way, weren't they? They weren't just sort of, hey, that's the other side of the galaxy or the next galaxy over. They were a long way away, weren't they?
We're talking billions and billions of light years away.
Okay.
And that was a bit worrying because for something to be billions and billions of light years away and for us to be able to spot it means it must be very bright.
Yeah.
Very,
because
very bright.
If it kind of looked like a star, but it's a really long way away, then that's a really, really, really bright thing. So what is it? What's a quasar?
Well, so when you do the sums and figure out actually how bright it should be, this might help a little bit, then it turns out that this one object in just the infrared turned out to be more than 100 times brighter than the entire brightness of the Milky Way galaxy.
More than 100 times brighter than the galaxy, the entire galaxy that we're in now. So that's a lot for a single object. Very energetic. What's going on?
Well, you could say, well, maybe it's just a very big galaxy or something like that, right? It's just a galaxy. It's 100 times bigger than our own, maybe.
Okay.
But we had a second piece of information, and that was that these quasars vary. And the timescales in which they vary give you the maximum size which the object can be that's giving this light off. And this is calculated by the fact that light takes time to travel. So if the variation that you're seeing in your object varies on timescales of, say, hours, then it can't be bigger than a few light hours across in size.
Right. That makes sense because it takes time. I mean, if the object, whatever the object is, whether it's a star or a planet or an entire galaxy, if it's changing over time, then that change, it takes time for a change in one part of the thing to make its way across to the other part of the thing and tell it that it's changing. So it can only be as small as the time scale of that change for light to get across that. That makes sense. Okay.
Yeah.
So over what time frame were these things changing?
So they vary on timescales of hours to days, which gives us a maximum size of this object of maybe a few times the size of the solar system.
Now, okay, the solar system is big, but it's not that big. And if you're talking about something which is hundreds of times brighter than the entire Milky Way galaxy in an area, let's call it roughly the size of the solar system, then holy cow, that's a lot of energy in one very small place. Yeah?
It is. It's insane. It's an insane amount of energy. And this is explained by what we now call an active galactic nuclei, which is a black hole that's beaming out this huge beam of energetic radiation, and it's sending that beam basically straight towards us, so it looks really, 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 really bright. And but it's only through the incredible amounts of energy that come from such a compact object as a supermassive black hole that you can generate that much energy in such a small space.
Okay. Now you're talking about this like, well, I mean, that's bloody obvious to anyone, supermassive black hole at the center of the galaxy. But when these things were discovered, was it sort of clear straight away that, well, of course, we all know what quasars are, don't we? Said the astrophysicist knowingly with a wink. Was that kind of how it went, or was it, what the hell are these things for several decades? Like, how did it go?
Well, somewhere in the middle. I think so. Obviously, when we first saw them, we were like, "Oh, wow, this is weird. Oh, okay, what's going on?" So it took a couple of decades to sort of nail down what was going on. So this is happening, over the maybe sort of the 50s, 60s, and then slightly into the 70s that we were putting this sort of puzzle together of what these objects were. And of course, keeping in the back of our minds that we had this type of object, which is described by GR as a black hole. And then came along a very, very interesting physicist by the name of Roy Kerr. And I have to mention Roy Kerr because he's probably the most famous physicist who I've ever met, and probably the most accomplished physicist I've ever met.
just a little name dropping going on here, then. Okay.
Well, I have to give him a shout out as well because he's a fellow Kiwi, so
Okay.
Good vibrations there. So in 1963, Roy Kerr took the equations of how you might generate a black hole, or looked at the equations of a black hole, which was kind of a very perfect, like if you took, it's like when you do introductory physics and you take out all the hard bits and you just make it the easiest object that you can possibly deal with. In physics, you often see, for example, we ignore things like friction because that's just irritating if you have to do all the calculations with friction in them. Or famously, you might take a cow and say, well, we're going to model this cow. As a physicist, you might just make it into a sphere because spheres are easier to deal with.
Yeah.
So you have spherical cows.
Yeah. Classic spherical cow problem.
And then you put them in a vacuum so that they don't have any friction. Yeah. So up until the 1960s, that was how we dealt with black holes. We just did the easy versions of them. But Kerr decided that we needed to take them the next step further. And so he started creating theories for rotating black holes. So before that, they didn't rotate, or we didn't have the maths to describe them rotating. And he went on to, well, he did first of all the uncharged, so they had no electrical charge, and then along with Newman did the charged rotating black holes and managed to solve those equations, which was a huge accomplishment. So like very, very clever stuff that they're doing there. And you find out all sorts of interesting things, all sorts of subtleties of black holes.
It's worth pointing out that, this is how hard the mathematics is, that we are now, 10, 20, 30, 40, about 50-ish years on from Einstein dropping the theory to, great, we're able to now figure out some details, some solutions about a rotating black hole, which is, it's just slightly away from the simplest possible solution that you can do to Einstein's equations, a rotating charged black hole. We're not adding a lot here. We're not talking about, a black hole going around a star, or we're not talking about black holes, accreting matter and destroying a nearby star or anything like that. We're not doing anything fancy. We're just trying to model this one object, which is a rotating electrically charged black hole. That's how hard this is, folks. It's really complicated stuff.
It really is. But now we can get to the bit you've been waiting for.
Hurrah!
So Penrose was following Kerr and Newman's work and their solutions, and he wanted to take that next step even further and say, well, let's assume that you don't have a black hole that's a sphere. You don't have spherical symmetry, or you don't have a spherical cow. You've actually got a cow-shaped cow.
That's getting really hard.
It's really, really hard. And so he had to basically, to do this, he had to basically invent a whole new mathematical tool to be able to describe this non-spherical symmetric black hole. And the mathematics he invented was the mathematics of trapped surfaces, which sounds really, really fun and very, very cool. So if you've ever seen kind of things like Escher drawings, MC Escher drawings, or if you've seen like Klein bottles, or these kind of impossible objects where they can't exist in the real world, but they can kind of exist mathematically and you can draw them, which I always find incredible.
Yeah.
Then trapped surfaces are a bit like that.
I was reading up on this before the show, and I'd always known, right, that Penrose, interesting guy, he was really into the general relativity and curvature of space-time, and he was all about the mathematics of spaces and how things do their thing in space-time. And I also knew that he was kind of into geometry in a big way, in all sorts of other ways. Like he's come up with interesting a thing called the Penrose tiling, which is a kind of, if you imagine tiles on your bathroom floor, normally in order to get a consistent pattern across the floor, you've got to have tiles which repeat, have some kind of repeating structure to them, repeating symmetry to them. And he's come up with a non-repeating but completely covering the plane tiling thing called the Penrose tiling. Like he thinks about those sorts of things. And I knew that the sort of stuff that he thought about was very similar to the MC Escher stuff, right? And Escher's all about, you must have seen the pictures of the never-ending staircase, where there's a sort of three-dimensional picture of someone going upstairs, and they go around the stairs, going up and up and up, and they come back to where they started from. And it's an impossible staircase because it just goes around in a square. It's going up all the time, and yet you come back to where you started from. Penrose and Escher actually kind of collaborated on those things. Penrose came up with some of the ideas and sort of wrote off to his new mate, Escher, and said, hey, what do you think of this? And Escher went, oh, I could draw that. That's really cool. Like, I had no idea that they were doing that right from the very beginning. I thought they just were sort of, they were existing kind of in parallel. But no, they were right there together. So Penrose was all about hey, let's see if we can come up with some really impossible things here. And along the way, he kind of went, hey, black holes too. It's really interesting the way the mathematics of that has kind of, I don't know, happened in parallel in his brain.
Yeah, it's quite interesting. So to summarize it, what a trapped surface is, it's obviously something that we can't sort of have in our normal three-dimensional existence. It's a bit like one of these drawings where it can exist mathematically, but not in the sort of three-dimensional space that we sort of operate in.
Right.
but a trap surface it's like having a slope where downwards always points towards the same place. And that doesn't matter whether you're at the top of the slope or at the bottom of the slope or round the corner from the slope. So imagine you had a cow and you had that cow in an absence of gravity, and you put a ball on the cow, then the ball would always end up pointing towards the center of the cow, no matter whether that was curved outwards or curved inwards. Does that work?
I think I'm following you. I think you've lost me with the latest. Like we've gone from spherical cow to real cow to now gravitational warped cow. No, I'm not sure that I'm following this.
All right. So a more mathematical way to say it would be all rays point towards the center, regardless of whether your curvature is outwards or inwards or any other shape.
Okay, and that shouldn't be.
No, that really shouldn't be. You don't have objects in your house which do this, which is a good thing.
No. But as you say, it's something which you can play with mathematically, and this is what Penrose did. This was his thing. Okay, forget about what you know around you. If we can come up with mathematical structures, maybe we can relate those through the physical theories to stuff that we haven't worked out yet. Maybe there's something in this. That was his thing. And so this new way of looking at the mathematics allowed him to tackle problems with general relativity that had been completely impossible previously.
Exactly. And so effectively he was able to use GR to construct what we now call a black hole, and I think the terminology sort of came up in the 60s when these people were working on it. And using this trapped surface, you could explain the short shield radius or the event horizon of a black hole, and therefore what happens, at least what happens close to the black hole without knowing, and we have no way of knowing what actually goes on inside of it. Because it really is this one-way system. Once you get to the short shield radius, once you're inside of that, then there's no way that any information whatsoever can ever leave that black hole.
So for his half of the Nobel Prize, it's almost tempting to imagine the discovery of black holes as being, from a theoretical point of view. Well, I mean, obviously, right, if you get enough mass, then it'll collapse down to its gravitational center and form a black hole. End of story. But the reason that Penrose is getting this gong this time around, the reason that they're throwing the award at him, is because he was responsible more than anyone else currently alive for being able to take an already mathematically incredibly difficult theory and finding new mathematical ways into it to say, well, if we look at it this way and if we formulate it in this way, then we can construct seemingly impossible objects in the universe, but they work and they solve problems. They allow us to come up with, a hypothetical object in the universe, which we can say, you know what, maybe these quasars, for example, maybe that's what we're talking about. It allowed him to come up with a way into these problems that no one had been able to do before. So it was far more than just, hey, black holes, what do you reckon? It was, I've got the formulation. Let's run with this. It was an amazing achievement. And that was back in did you say in the 1960s that all that really kicked off?
65, yeah. And of course there's really broad applications of this beyond just black holes as well. Famously, Penrose went on to work with Hawking on other cosmological singularities, including mini black holes, including the Big Bang, which is kind of a singularity like event singularity event. It is a singularity event as well. So it laid the foundations for a lot more theoretical physics to come after the 60s as well.
Yeah, it kind of opened the floodgates on a whole bunch of stuff, which requires a really deep understanding of how general relativity and the curvature, the warping of space and time, the fabric of the universe, when under extreme conditions, what does that do? How do you even deal with that? And that's what his mathematical achievements allowed people to do from there on in. So great, well done, Penrose. That's half of a Nobel Prize, but it's only half of a Nobel Prize. So shall we talk a little bit about the other half?
Well, yeah, just like all good science, you've got to have not only your theory, but you've got to have your observations, your experiments, which test and confirm, deny, or question your theory
Yeah, exactly.
as well. And so the other half of the Nobel Prize is shared between two people who went out and found evidence of the supermassive black hole, which is in the center of the Milky Way galaxy.
Right. So going back a little bit, you were talking before about quasars and these incredibly energetic things, enormous distances away, like ludicrously redshifted. So you could guess, you could hypothesize, you could make a pretty good astrophysical, guess that says the only thing that could conceivably be that bright but having variations in the order of hours or days, the only thing that could possibly do that is in an enormous black hole, right? But you can't go and actually find that thing. Like, it's so far away that all you can really do, I guess, is just look at a really bright, energetic object and make some assumptions.
Yeah.
But that's not what you can like. You can do something different in our own galaxy, though, because in our own galaxy we've got a chance of actually seeing stuff, right?
Absolutely. And here we've got to make kind of quite a big distinction between the quasar objects that we were observing, that we observe in very distant galaxies, and the supermassive black hole in the center of our galaxy. Because our supermassive black hole is not a quasar. It's not feeding, so it doesn't have these really bright, energetic outputs. Instead, it's kind of the opposite. It's a black hole. It's an ordinary, if you like, supermassive black hole. And it's not pumping out all this extra energy. So it's much, much harder to then detect because it's not putting out any light at all.
So can I just ask, what's the difference? Like, why would one supermassive black hole be ludicrously energetic and another one just not be obviously there, and it's supermassive, it's really, really, really big, but it's not particularly energetic at all? What makes the difference?
Yeah, so it's the feeding. So it's whether you've got material which is actively falling into the black hole. And when that material falls into the black hole, some of it kind of slightly misses and gets repurposed as energy shooting out in these enormous jets. And those are the bright objects that we see with the quasars. Our supermassive black hole isn't feeding at the moment. It's just quietly sitting there. So it's not tearing stars apart. It's not tearing planets apart. So it doesn't have any way of generating light.
So, but that could happen in the future. Like, it's possible that some material gets a bit too close and starts getting pulled apart, and it does kind of kick up to quasar level.
Yeah, and we actually have evidence that it happened in the past as well, that at some point the Milky Way did have a jet, maybe not as strong as a quasar jet, but at least something that was fairly energetic.
It happened.
So it just happens that we're in a quiet phase, which is probably a good thing.
That's good. Let's keep it that way for a little while. So, how long have we known or believed that there was a supermassive black hole at the center of our galaxy? Because there's a leap there, right? There's a leap from, hey, that quasar, the only thing that I can think of conceivably that could be doing that is maybe a supermassive black hole at the center of that galaxy. And maybe there's one at the center of our galaxy too. There's a leap there. So when did we do that?
Yeah, so we quickly, after the discovery of quasars, put together an understanding that there should be something central, big, supermassive object in the center of all galaxies. And that was also being confirmed by things like observations of how galaxies rotated. So you need to have big mass in the center for those things to rotate at the speeds they do. So even since the detection of quasars, it seemed fairly likely that all galaxies, including our own, should have this kind of object in the center. And it was that object that these two Nobel laureates, Genzel and Ghez, went out to actually find. Can we find some observations which confirm its existence?
So how do you find it? That seems like a ludicrously impossible thing to do.
Yeah, I mean, it's crazy, but we don't have any light coming from this object, so we can't just sort of point a telescope and see what happens. But it does have one other property that is very, very important, and that is it's got a lot of mass. And, a supermassive lot of mass. So that means that mass has to have some effect.
When you say supermassive, like how How supermassive are we talking?
So for our black hole, we're talking maybe around 4 million times the mass of the sun.
Wow. Okay. So that's okay. That's a lot of mass, right? If you consider that we are currently here on planet Earth in orbit around a not particularly big star, the sun's gravitational influence on us is pretty apparent. Okay, so if you've got millions of solar masses clumped together into one object, then that can have an enormous impact on anything nearby. So is that how you go searching for it then? You look for that gravitational influence on stuff nearby.
Yeah, and it sounds like it should be an easy problem, right? If we can detect the sun pretty easily, then we should be able to detect 4 million suns.
Piece of cake.
It should be, it should be.
Come on.
It should be fine. It turns out that the problem is not so much what it is, it's where it is. It's in the most awkward place for us to go and make these kinds of measurements, which is in the center of our galaxy.
Why is that so hard?
Well, imagine looking at the Milky Way when you see it on a nice dark night, right? You see this kind of band of stars and gas floating across the sky. And where the center of the galaxy is the highest concentration of stars and gas and dust that you're trying to look through. The problem is that there's so much, particularly dust, in between us, about 2/3 the way out in our galaxy, and the center, that in the optical, then only one photon in a billion gets through that dust from the center.
Right.
One
Okay.
in a billion.
Yeah, I mean, on the one hand, you'd kind of like, well, I mean, it's the center of the galaxy, so surely that's the easiest bit to see because it's the really bright, dense bit, but it's the equivalent of standing sort of towards the edge of a really big forest and looking through the trees towards the center of this really big forest, and you can't see the forest for the trees. That's all the trees are in the way. And in this case, all the stars and all the gas and all the other stuff of the galaxy is hiding the very thing at the center of the galaxy that you're trying to see. So, okay, this has just gone from surely that shouldn't be too hard to that's impossible, Emily. There's no way that you could possibly see that. So how do you do it?
So the key to this is you need to not look in the optical. You need to go to the infrared part of the spectrum, because it turns out in the infrared, then most of this, particularly the dust, is fairly transparent. So in the infrared, you're down to just 1 in 10 photons can get through the dust, which is much, much better than 1 in a billion.
That's better. I mean, it's still not a lot, 1 in 10, but that's all right. That at least gives you a fighting chance of seeing something. All right, so when you go and look towards the center of the galaxy, and I'm assuming, by the way, that astronomers are clever enough to be able to pinpoint, even if we can't see exactly what's there, we can pinpoint where the center of the galaxy should be. Like we know where to look. That's a doable thing.
Yeah, actually, that's a good point. Yeah. So Shapley, one of the astronomers, that would have been at least 100 years ago, figured out that the center of the galaxy should be in the constellation of Sagittarius.
Okay.
So we kind of knew roughly that should be where things were happening. In the 1960s, we started to get signals that showed there was a very strong radio source in that location. And so the radio is to do with the fact that the black hole is there. So it's an indication that there might be something interesting going on there. And so at that point, with this object at the position of what we now say is the center of the galaxy, we call Sagittarius A star,
Right.
meaning it's kind of it's probably a black hole.
It's special. It's special. But there were signs pointing in that direction, right? We know it's up here, and hey, turns out there's this quite energetic, not sort of quasar level by any stretch of the imagination, but there's something up there. It's spitting out a lot of radio waves. So maybe that's what we're looking for. So we know where to point our telescopes. Great. And we know that we need to do that not in the visible. We want to go down into the infrared, because at least some of those photons get through. Great. So what do you see when you look?
Well, yeah, we had to even to get to the point of looking, we had to start to get really clever. And so this is where our two laureates come in, because each of them set up an independent team of researchers, an independent research program to try and push our best telescopes in the world to the absolute limit to try and get images of this very, very central region. Because it's one thing needing the technology to be able to observe in the infrared, that all sort of mostly came through in the 80s. But then we needed to get resolution, so that means we needed to get really big telescopes. Reinhard Genzel, who is in the Max Planck Institute for Extraterrestrial Physics, he was set up looking at something called the New Technology Telescope in Chile, and then later on moved to the VLT. We've talked about the VLT before, the Very Large Telescope, also in Chile, which is 4 8-meter mirror telescopes. Huge, lovely telescopes.
These are big honker. I mean, it's in the name, right? The Very Large Telescopes. So we're talking. I mean, these are reasonably recent devices. We're talking what, the 1990s is when this started. Is that right?
Yeah, from the 1990s, this sort of became within the realms of possibility. I wouldn't say it became possible because there were a lot of hurdles to get over, but it started to look like this might be a thing we could do.
I like that. You're pushing towards the realms of conceivable. We maybe could do this. And that's, you're at the cutting edge when you're using that kind of language.
Yeah. And similarly, Andrea Ghez in the University of California set up a program working with Keck. So Keck is 2 10-meter telescopes that are in Hawaii. And that's okay, cool. So first thing is you need big telescopes. Check, we got them.
Okay, got them.
But second problem is because you need this incredible resolution, is that you can't put these telescopes in space. You can't put 10-meter telescopes in space, and we needed really long observations, and so space telescopes just weren't going to cut it. But the problem is when you do this from the ground, then we've got basically a soupy atmosphere that we're trying to peer through out into the universe. And this is hugely problematic.
It's putting it mildly.
Yeah.
Okay.
Yeah. So it was a huge technological challenge. So we needed new ways of dealing with the fact that we've got this kind of soupy atmosphere above us that's distorting all the images that we get from the center of the galaxy. And two really important developments which made this kind of research possible were first of all speckle imaging. I don't know if we talked about speckle imaging. It's a nice technique.
I do seem to remember. Yeah, remind me what speckle imaging is.
So speckle imaging is where you, instead of sort of opening up the shutter on your camera, and if you need to do a 30-second exposure, opening up the shutter, waiting 30 seconds, and then closing it again. Now, if the thing you're trying to take a photograph of is moving, as would a star would move as the atmosphere moves, then you just get this blurry smudge, right?
Yeah.
So speckle imaging, instead of taking one 30-second exposure, takes 30 1-second exposures. So very, very short, sharp images. But each of them isn't bright enough on its own, but when you stack them, when you overlay them on top of each other, you can sort of move them around so that they're perfectly aligned, and then you get a nice high-resolution picture of your star.
That kind of sounds like witchcraft and wizardry to me. You can't take a 30-second exposure, but you take 31-second exposures, and suddenly all the noise goes away. But is the witchcraft coming in the, but we can line them up properly so that rather than having a 30-second exposure, which is all washed out, if we line them up by presumably finding the bright bits and lining up the bright bits that are quite clear, then that allows us to cut through the noise. Is that the idea?
Yeah, it's like if you had an old-fashioned stack of overhead transparencies and you had a constellation on all of them, but all in a slightly different place each time, then you can move all the transparencies until they overlay, and then you get this nice stacked image.
Clever. All right, so that allows you to cut through some of the noise. Good.
And the other one, of course, was adaptive optics. And this was, I guess, one of the hugest developments in astronomy over the last 20, 30 years. So this is the ability to undo the effects that the atmosphere has on your observing in real time. And this is the cool high-tech astro stuff.
Yeah. Now you want to talk about witchcraft and wizardry. This is it. Yeah. Is this the one where you shine the laser up through the atmosphere? Is this the one? And
It is,
how
yeah.
does it work?
So what you have is you have so your star is wiggling around, and you can't predict how it's going to wiggle around, but you want to correct its wiggling around afterwards, right? But you don't know how much of the wiggling might be intrinsic to the star itself. So you can't just undo an imaginary wiggle. But if you can create a fake star, a star that's perfect, that's not going to wiggle, or it doesn't have its own wiggle, then you use a laser. And if you use a laser to create an artificial star, then you know that the laser that's created that star is perfect, that star should be perfect, it shouldn't move. Of course, when you put that laser into the atmosphere, then it does move, and you can measure your movement of your control star or your laser star.
That's so clever. So you've got...
What's amazing about that then is that you take that movement that you've measured from your laser star, and you deform your secondary mirror. So you've kind of got this like wobbly secondary mirror. So instead of being perfectly smooth, you actually change the shape of your mirror in live, real time to undo the atmosphere's effects on your star.
I mean, that is absolutely bonkers to be able to do that. And to do that on, like, these aren't small telescopes. These aren't just sort of little backyard telescopes. These are big honking telescopes, right?
Yeah, it's amazing. Yeah. So in real time, you were just undoing the fact that the atmosphere is there. And so these telescopes are able to get similar resolution to Hubble.
Wow.
Which is in
wow.
space.
By shining lasers up and pretending that laser is a star and comparing it against, well, we know what the laser input was because the laser's right here. We know what that laser's doing, and so we can correct. So we've got the optics. You're deforming your mirror, and you've got what was the first one?
Speckle imaging.
Oh yes, so you got the speckle imaging, and you've got your deforming the mirror, and both of those things allow you to remove a lot of the noise and the gumph and allow you to see more clearly through to the center of the galaxy. So when you do that, what do you see? What happens?
So this is quite exciting. So these groups were looking at very, very special stars, which we call squeezars.
Squeezars is a good name.
Squeezars. So squeezars are stars that are close to the supermassive black hole. The most famous of which we have talked about before, all the way back in episode 16 of Syzygy.
Wow, that is going a long way back.
Is a star called S2.
Was it called a squeezar?
I
do remember S2, but I don't. Did we call it a squeezar, or is that a new name?
I think squeezars might be a new name, but
we might have to do an
so
episode on squeezars.
Go with this now.
Okay. So let's not spend too long on squeezars. I think we might keep that for another time. But S2, I do remember. S2, if I remember correctly, is in orbit around the black hole, Sagittarius A star, the thing that we think is the big black hole, and it goes really close.
It does, yeah, and it takes 16 years to go around in its orbit because it's so close to the black hole. To compare, we take like 220 million years to go around the black hole.
Yeah, so 16 years might seem a really long time, but trust me, for a star to go around in its orbit, that's real quick. That's really, really quick.
Yeah.
So quick that when on its closest approach, doesn't it go some ludicrous speed? Like just madness. Isn't it like thousands of kilometers a second or something?
Yeah, so you're talking about fractions of the speed of light by now.
That's mad.
Yeah.
For a star.
So S2, we talked about in episode 16 because it completed, we were able to observe its entire 16-year orbit, which was really exciting. So we completed the whole orbit, and it went to its closest approach to the black hole twice. We were able to do some really precise measurements of how fast it was going, and we were actually able to measure not only the mass of the black hole very accurately, but also test general relativity theory as well, because enormous mass has an enormous effect on the space-time around it. So you need to make sure your GR equations are holding up to that. And they absolutely were.
Double bonus. So you can pin it down, you can see where it is, you can tell how massive it is, and give general relativity a bit of a test while you're there at the same time. I've actually just pulled up the image of that orbit right now with all the measurements and stuff on it, and it is pretty staggering. I mean, it says on here, S2 reaches its maximum velocity at closest approach to the black hole. 7,000 kilometers a second. Like that's nuts. This is a star. Like, that's insane. Wow. Okay. So were both of these groups, because there was one based in America and one based in Germany, were both of these groups looking at the same star? Well, like, were they kind of collaborating on this, or were they competing on this, or were they looking at different things? What were they doing?
I think, a bit of both. So both teams use obviously different telescopes and some very slightly different techniques, but both were able to observe the same objects and draw the same conclusions, and all of their results matched up really well. So this is why the prize is joint, because they both succeeded, I guess, in this discovery and this ability to say, actually, hang on, we've got this star, it's going around at such an insane speed, we can measure the mass, and they get the measurement of the mass of this 4 million solar masses of the supermassive black hole. And we know that, this is happening in a region which is more or less the size of the solar system. So, although I think in the citation for the Nobel Prize, they don't call it a black hole, they call it a supermassive compact object, I think we can all pretty much just read
hedging their bets still.
Read black hole there.
Short of some more interesting new physics. Let's just cut through the crap here and we'll just call it a black hole. Shall we? Shall we do that? I mean, I love this notion of, these stars orbiting in ways that stars really shouldn't move. This is not something that your average common or garden variety star ought to be doing. Around an area of space where in every other way, other than maybe sort of, radio waves and so on, like there's nothing there. It's not like this, hey, look at that big bright thing in the middle there. They're all going around that. That must be it. No, but it's just sort of kind of blank. Like that's really, really cool.
It's almost spooky, isn't it? See, you used to see planets going around a star and you think, oh yeah, that's a normal thing for them to do. But then when you see stars going around nothing,
that's pretty bonkers.
A bit odd.
All right, so to recap then, this year's Physics Nobel Prize went for the discovery, theoretically, and then experimentally, observationally, of black holes. Penrose for going, hey, Einstein, give me those equations. I can wrangle those in a different way. I'll pull in a little bit of MC Escher stuff with impossibly ridiculous mathematical spaces that shouldn't exist and yet apparently do, a bit like black holes. Here you go. Here's your solution. And a couple of observational astronomers who went, you know what? I reckon there's one in the center of the galaxy. Let's go find it. Oh, you know what? That's going to be really, really, really hard. Don't worry about it. Biggest telescopes on the planet, bit of adaptive optics, bit of speckle imaging, and there we are, stars whipping around at thousands of kilometers a second. That must be the black hole right there. That's your Nobel Prize for 2020. And look, fair play. I reckon that one deserves it. I'm also going to say that next year's, and probably the year after, is probably not going to be general relativity, black hole, or maybe even astronomy, astrophysics related. I think we're probably done with that for the last decade. Emily, what do you reckon? This is...
I don't know. We got a nice image of a black hole there, Chris.
Well, that's true. That's true. That could happen.
Yeah,
that could be the next one.
Pretty ground-shaking observation.
Yeah.
This is, of course, the first image that was made of a black hole that came out in 2018. Is that right?
That's right. And actually, everyone was expecting that to be image of this black hole in the Milky Way, weren't they?
Yeah.
And then that one didn't work quite so well. But we got the image of the other one instead.
The one that we had the image of was M87, which is 1,000 times more massive than the one in our Milky Way, and also not in the middle of our Milky Way. So yeah. I think they're working on...
So in a way, easier to see.
They're working on the one in our Milky Way.
That would be amazing.
But but don't worry. There's still lots of black hole physics that you can earn more Nobel Prizes for if you want to.
Okay. So if I wanted to go and get myself a Nobel Prize for black hole physics, what have I got to do? Right? We've got the maths, and we've pretty well spotted it in our galaxy. So what's left? What have I got to do?
There's still some interesting things. So in terms of our Milky Way black hole, there are some flares which seem to be going on, which we haven't quite been able to resolve because they're happening on just towards the center of where these orbits are happening. But we do have some evidence for flares that might be interesting. So it could be a direct measurement of something happening close to the black hole.
Okay.
Have to see how that goes. There's, of course, the chance to do more precise tests of general relativity. You turn everything up to 11 and try harder to break general relativity, see if it does break. If you break it, then I think that's going to be quite revolutionary.
Yeah, definite Nobel Prize there for breaking general relativity. Yep.
But if you want to really crank it up and, not just win one Nobel Prize, but probably several, then you can sort out this quantum gravity problem.
Yeah. Yeah, that one's waiting in the wings. Now, the big problem there, because so far, right, Einstein's right. Yeah, you hear every once in a while a headline which is, has the following experiment/theory proven Einstein wrong? And the answer to that is invariably no, because every test that we've ever done of special and general theories of relativity has always come out, yep, pretty much spot on. But there's a problem, isn't there? Which is that the other big theory that revolutionized physics and our understanding of the universe from about 100 years ago, which is quantum physics, it doesn't work. When you put the quantum thing and the relativity thing together, it all breaks. It doesn't work.
Yeah,
and yet they're both incredibly accurate, precise, and well-defined, well-tested theories of the universe. They're both right, but they can't both be right. So there's got to be another answer here. There's got to be a way to tie these things together. Maybe it's something completely new. We don't know. But whoever gets there is going to have awards piled on them faster than you can point a stick or something.
Yeah, it's the old square peg in a round hole, and you're absolutely sure you've got a square peg, and you're absolutely sure you've got a round hole.
And yet somehow that peg's got to go through that hole.
It just doesn't get in there, and you're like, what is going on here? Maybe we just need another universe to make them fit.
Yeah, greatest minds in the mathematical and physical world have been working on this for decades now, and I don't know. I mean, it's jury's out as to whether or not we're even getting any closer on that problem. So yeah, that would be a big one. So if you can go and solve that one, dear listener, I will personally recommend you for a Nobel Prize. There you go. How about that? You're not going to get a better offer than that today.
Yeah, and so I think the last thing to sort of reflect on is a little bit of the human side, I think, of the Nobel Prizes. Because Nobel Prize is not without its own controversies, right? It was always, why didn't Einstein get one for GR? Why didn't Hawking get one?
Yeah.
And now he can't because you have to be alive to get it.
No, you can't because
et cetera, et cetera.
The Nobel Prize is not given posthumously. And it's a very weird exercise, right? That you're picking out of all of the research that goes on in any given year, or indeed decades, because, Penrose, the stuff that he's getting this for happened many, many, many years ago, right? But you're picking out individuals, or at best representatives of groups, for a prize. I mean, it's a bit arbitrary in many ways.
Yeah.
You're picking out these representatives of science and saying you deserve an award. It's a weird thing.
And I think you can draw a lot of criticism of the Nobel Prize process, but regardless, there is an amount of a Nobel Prize is our cultural kind of Academy Awards for sciences, and it just holds that in our society. So I think a really important thing this year was that one of the recipients in physics was a woman.
Yeah.
So that was very, very exciting. So Andrea is only the fourth physics laureate to be a woman, which was, this is out of 200 odd, people that have had it over the last however long the Nobel Prizes have been going.
Yeah, in the order of 100 years, yeah. So on the one hand, that's a really good milestone.
Yeah, although it shouldn't be, we should be moving closer to not having that be the milestone, but being the norm. But of course, until we get to such a point, we need to celebrate diversity as much as we possibly can. And Andrea's already, kind of stuck her hand up and saying, you know what, if I can be any kind of role model to young women in STEM, then I will absolutely take that very seriously and, do my very best to promote science to young women, because we obviously do need more people working on these things. And I've said it before, and I do truly believe it, that the more diverse people you have, the more diverse ideas you have, and the closer you get to solving problems.
Well, that brings us through the 2020 Nobel Prize extravaganza. It's been a black hole-filled episode here today. Emily, there's some big stuff here, but I fully agree with you. I think, look, on the one hand, having one of the Nobel Prize winners in physics this year being a woman is, it's a great thing, and it's representation where it is absolutely needed. On the other hand, for her to be number 4 in the history of the physics Nobel Prizes, we've got a very long way to go. But I was really interested to see that the chemistry Nobel Prize in 2020 did go to 2 women. It was they developed the tools that edit DNA, what's called the CRISPR-Cas9 genetic scissors technology, and it was given to Emmanuelle Charpentier and Jennifer Doudna, and these 2 women shared the chemistry Nobel Prize this year. And so I'd like to think we are moving in the right direction in science, in being able to recognize achievement wherever it happens and to be able to push forward talent in all possible ways. I don't know. I'd like to think that that's where we're going.
We could have at least as many women as we do have Brians. That would be nice.
Oh, listen, on that note, let's find our way out of this episode. If people wanted to get in touch with us here on the show, Emily, how could they possibly do that? Is there a way that people could get in touch with us and, for example, correct our understanding of black hole theory and experiment? Is there a way that they could do that?
No.
But what about through the interwebs? Surely there's something.
Oh, right, yeah, no, of course, the internet is a thing, right, yes. Of course, yes, we are on Twitter. We are at SyzygyPod, that's at SYGYPOD. Same goes for Facebook, Instagram, and there's no new social media popped up in the last kind of week.
Not that we're involved with. I'm far too old for anything new that's come along in the recent couple of years. But we do have a website. We have a website that people can go to, syzygy.fm, where you can go and find our past episodes, all of the show notes, all of the good stuff, and even go back as far as episode 16, where we were talking about what were we talking about in episode 16? My brain's just gone blank.
S2.
What did we talk about?
S2.
Oh, that's right. All the way back to episode 16, where we were talking about S2 whipping its way around Sagittarius A star. So you can go back and have a look at all of that. And you can find our comments page, where you can send us a form with some questions, some ideas, some thoughts, even just say hi. A couple of different ways that you can support us here on the show. The best way is just to tell everyone you know. We'd love more people to share in the excitement and joy that we get from exploring the universe every week. So if there's someone in your life that you think they'd get a kick out of listening to Syzygy, then point them in the direction of our podcast. We'd be forever grateful. The other thing you can do is become a financial supporter of the show. Everyone who kicks a bit of money our way through patreon.com/SyzygyPod helps us to keep the electrons flowing and the lights on here at Syzygy HQ. And when the world does eventually open back up again, allows us to go and do things like festivals, live shows, all of that sort of thing. So if you could pitch in and throw us a quid or 2 every time we spit out a show, that would be really, really helpful. Thank you to everyone who has done that so far. Otherwise, Emily, I think we've got a bit of an idea for a future show. Shall we talk about squeezars sometime?
I think we definitely need to look into squeezars. And here, I'm going to blow your mind. I think we can also talk about planets.
Squeezars and planets? Okay, we have a show. We will be back again in a week or 2's time. But until then, Emily, I'll catch you again soon.
See you later.
Bye, everybody.